In this video, we'll learn about the Atomic Absorption Spectroscopy, also known as AAS. Now, this is an important analytical technique in chemistry, and it basically allows you to measure the amount of light being absorbed by a sample solution. Now, using this, you can calculate the concentration of metal ions in a sample solution based on its absorbance of light. Now, to find the concentration of any metal ions in a solution, you first need to construct something called a calibration curve. So, draw a calibration curve. And to construct a calibration curve, you must first create a series of standard solutions to the metal ion, and then measure the absorbance by AAS. So you will be given a table of values with, let's say, absorbance and the concentration of a metal ion. Say, for example, the concentration of mercury. And you'll be given a table of values that looks like this. And you might be given something like the absorbance of, let's say, 0.026, 0.053, 0.078. Then you'd be given a sample. And then the concentration of mercury would be like 1, 2, 3, and 4. And you'll be asked to find the absorbance of the sample. Okay. Now, first what you need to do is you need to plot this in a Cartesian plane. So let's say we have the first quadrant. So we'll only be focusing on the positive values of x and y. Label. So the concentration goes on the bottom for mercury. And then the absorbance goes on the y-axis. Okay, and goes up to, let's say, 0.01. Label that as 0.1. Let's say that's 0.5, 0.75, and 0.25. So that's 1, 2, 3, and 4. Now we plot these points on the Cartesian plane. So when x is 1, y is 0.026. So that's around here. Okay. When x is 2, it's about 0.05. Sorry, 0.05. So that's around here. When x is 3, y is 0.07. It's around here. And we have sample, so 4, and we don't know what the sample is, so we'll leave that blank. Now what we need to do is that we need to connect the lines. Okay. So try to connect it in a straight line, like that. And that will be our calibration curve. So to find the absorbance of the sample, what we need to do is we need to first draw a perpendicular line from x equals 4. Like that. That's perpendicular. And it will meet at a point of the line. And then draw a horizontal line that is perpendicular to the y-axis and it touches the point on the calibration curve. Now this point will be the corresponding y value for x equals 4. Now that would be approximately 0.08. Let's say it's 0.08. So we can write that the absorbance of the sample is approximately 0.08. And usually the concentration will be measured in milligrams per liter. So liter 1. And that's how to calculate the absorbance or the concentration of an unknown solution. Okay. So let's try another example. Let's say we were given a table of values that looks like this. The concentration of potassium ions, the absorbance, So we had 5 values there. So that's 0, it's 2, 4, 6, 8. Let's say that's 0.01, 0.08, 0.15, 0.21, 0.27. Now the question might say, use the calibration curve to determine the concentration of potassium in milligrams per liter in a sample solution that gives an absorbance of 0.17. So that's right on the bottom. So that's as a sample, 0.17. Okay. Now, first step, we need to create a calibration curve. Let's draw the y-axis and the x-axis. It doesn't have to be perfect. It's just an approximation. So that's 8, that's 4, 6, and 2. It's obviously 0. And then say that's 0.3 up there. And this is 0.15. So yeah, there we go. And now let's plot the table of values on the graph. Don't forget to label, by the way, concentration, potassium ions, and the absorbance. Alright, so when the concentration is 0, the absorbance is 0.01, just like right there, dotted in red, right there. When it's 2, it's 0.08, so it's approximately around there. When it's 4, it's 0.15, so it's there. When it's 6, it's 0.21, so it's around there. Okay, when it's 8, it's 0.27, so it's like right there. Now we connect the line, connect the dots. What are points? Connect it like that. Make sure to connect it in a straight line for now. And now what we have to do is we need to find the concentration of potassium in the sample solution. Now we know that the absorbance of the sample solution is 0.17. Now let's mark 0.17 in green. So 0.17 would be around there. Now we draw a line that is perpendicular to the y-axis until it meets the curve. Right there, meets there. Then you draw a line that is perpendicular down. That's around there, and that's approximately 5.5. So we put that 5.5, and now we can write the concentration of potassium ions in a sample solution. Sorry about my handwriting. In a sample solution with an absorbance of 0.17 is 5.5 milligrams per liter. Okay. Now, another way of solving this type of question is by using your calculator. So if you have a graphics calculator, you should be able to go to a menu that says statistics, and you would be given a list, with a table of values. So it may be like list 1 and list 2. So what you want to do is enter your table of values inside the calculator, so like 0, 0.01, 2, 0.08, 4, 0.15, 6, 0.21, and so on. Then you want to click on graph 1, and go to calc, then click X, and choose the option with AX plus B, Y equals, and you'll be given a list. You'll be given your A and your B values. So in this case, our A is 0.07 and B is 0.01. Okay, so that line is basically Y equals 0.07 X plus 0.01. Now what you can do is you can substitute Y equals 0.17 into the function and solve for X to find the to find the concentration of the potassium ion in your sample solution. So let's do that. So that's 0.17 equals 0.07x plus 0.01. That is equal to 0.16 equals 0.07x. So x is 0.16, 0.07. And that is equal to approximately 2.28. So our calibration curve is slightly off, but that's okay. 2.29 milligrams liter per liter. That's weird. No, we did something wrong. Oh, wait. 0.17. Shouldn't be. Oh, okay. I entered the values wrong in my calculator. Sorry about that. Let me fix that. I'm slightly off. Let's do it again. Okay, there we go. So the A value is actually 0.0325. B value is 0.014. Now, so our actual graph would be 0.0325x plus 0.014. Still do the substitution, and we should be able to find x. So I'll just do the substitution really quickly. Pen's so laggy. Okay. 0.17 equals 0.0325x plus 0.014. 0.7 minus. So that will be 0.156 over 0.0325 equals x. And that is equal to 4.8 milligrams per liter. So that's only 0.7 of our estimate, which is alright. And that would be one of the more accurate ways of calculating the absorbance or the concentration of the metal ion in a sample solution. Now let's look at another example. This will be a harder one. Now this will be one of the harder questions in your exam. So the question goes, iron is essential to our health. To determine the iron content in a Milo milk drink, a 5 milliliter sample was diluted to 50 milliliters. The absorption of the diluted solution and of several standard solutions was measured using AAS. The results are shown in the following table. So first piece of information, 55 milliliter of Milo diluted to 50 milliliters. So we added 45 milliliters of water. And we're given the following table of values. Solution, concentration of iron, Fe in parts per million, absorbance. We have 0, 1, 2, 3, 4 sample. We have 0.01, 0.08, 0.15, 0.22, 0.29, and 0.19. Now we'll use the calculator method we did before. So if I was to find the A and B value of y equals x plus b, the A value would be 0.07. I just did this on my calculator. B would be 0.01. So the trend line that fits this table of values would be y equals 0.07x plus 0.01. Now to find the concentration of iron in our 50 milliliter sample, we would substitute y equals 0.19 into the equation. So put 0.19 equals 0.07x plus 0.01. So 0.07x is equal to 0.18 and x is equal to 2.57. That's in parts per million. Now that's the first part of the question. Now the second part goes, calculate the concentration of iron in ppm in the undiluted Milo. So we're trying to find the concentration of iron in 5 mils. Now you noticed how we diluted our Milo by a factor of 10 before. And we calculated the iron concentration as 2.57 parts per million in the 50 milliliter sample. So since we diluted the Milo to 50 mils, the concentration of iron in 5 milliliter would obviously be greater than the concentration in 50 mils, because there's more water in 50 mils than 5 mils. So what we have to do is divide 2.57 parts per million by 10. Times by 10, because there would be a greater concentration of Fe, iron, in 5 mils. So the concentration of Fe in 5 mils would be 25.7 parts per million. Now let's move on to part C, which says determine the mass of iron you would consume by drinking a 250 milliliter glass of Milo. So first, we need to assume that a milliliter of Milo equals a gram. That's the first step. Now the second step, that we know that the concentration of iron in 5 mils of Fe in 5 mils equals 25.7 parts per million. So that's basically saying there's 25.7 grams of Fe per million parts of Milo, or million grams of Milo. Okay, now that becomes very important, our next step. So what we're going to do is we're going to scale that down to 250 grams. So to get from million to 250, we divide by 4,000. Now, so what we need to do for the other side is do the exact same thing. Divide by 4,000. And that is equal to 6.425 times 10 to the negative third grams of Fe per 250 grams of Milo. So basically we can say that's 6.425 milligrams of iron you would consume by drinking 250 mils of Milo. Now let's move on to part D. Part D states the recommended daily allowance of iron for people over the age of 11 years is 18 milligrams. Calculate the percentage of your RDA that a 250 milliliter glass of Milo provides. That's very easy. We do 6.425 over 18 because that's the recommended daily allowance. Now we times by 100 to make it into a percentage. And that is 35.56%. Okay. Now part E and F, there's just short response. It says the 0.0 parts per million standard, which contains no added iron, gave a small absorption reading. Suggest an explanation for this. So our original table of values, it had 0.0 parts per million equals 0.01 absorbance. So now the reason for that could be maybe something like the water that was used to make the Milo contains some iron in the first place, which is why the absorbance was 0.01 instead of 0. Now that would be an answer to part E. Okay, and for part G, it says suggest why the sample of Milo was diluted in order to measure its absorption? Now the answer for that would be like the absorbance range could have been outside the calibration curve if it wasn't diluted, and also maybe because the solution could have been too thick to spray into the flame. So remember how the AAS is measured by spraying a sample solution into a flame. So maybe if the solution is too thick, you can't spray it into the flame, maybe something like that.